Okay, so handed back your free response, and I tried to just look at the rubric and grade it as the rubric states. And so some of these, we're just going to go through exactly what that looks like. And so the highest you can get on each question is a 4 for like the free response. That's what it's out of, like 0 to 4. And so we're going to go through and like look at the little things that start counting you off to make it like a 3 or a 2 or a 1. So it's pretty hard to get a 3 or a 4. You can pretty easily get knocked down to a 2. And then if you don't have that good of a response, easily knocked down to like a 1 or a 0. And so we're going to go through it. And yeah, so that's what we're going to do today. And then starting, I'll see you tomorrow. We're going to do like 3 days of a bunch of practice through the different units on the year. So like y'all are going to kind of go through it in groups, and it'll be some multiple choice and free response, and we'll go through that. Okay, so I still have on the board the AP scoring. So I handed out the little rubric that I'm going to go through. You don't have to, I'm going to go through it so you could look at it too, but you don't have to. So the way I have it is at the top here, I'll have like part A question, and then this is on the rubric, the scoring for this section A. So they have scoring for every little part A, B, and C. And the way it works is you can get an essentially correct, partially correct, or incomplete. So essentially correct is like the best, then it goes partial, then it goes I for incorrect. So if you get a bunch of I's, you're getting a 0. If you got all E's, you get like a 4 on the question. And then there's a bunch of mixtures. Yeah, let's see. So what else? I think that's about it. And then YouTube, like they've got the live review sessions. On College Board, they've got daily videos for the entire year. Bunch of different stuff. But we just don't have a ton of time in class, so taking time outside of class to kind of look at some stuff too. Okay, so let's look at this first one and look at some ways where a lot of y'all kind of all got similar points off. So on this first one, there's like a paragraph up above about like group R, is it? Yeah, group R needed time to learn the program, and group S kind of already had used the program. And so they asked you which one of the 2 histograms is more likely to be group R and justify your answer. So here's what you needed to be essentially correct. So this is how they do it every single rubric, is they say essentially correct, and there's typically like 3 or 4 things that you needed. And if you get all 3 of these, then you get an E. And then you can see for partially correct, if you get component 1, if you get component 1 correct and one of the other 2 components. So like, let's just look at it. So if you stated that histogram 2 should represent group R, then you got part 1 correct. Part 2 was like why did you choose that? And it's the fact that group R, it took them, like in the paragraph it said that it should take them longer. I highlighted it, let's see. They needed more time to learn the program and to complete the task. So that's why I chose histogram 2. So if you have that, and it says, here's where most people didn't get full credit for this one. Justifies the choice. You could say, it says based upon the location of peaks or ranges. Basically, if you were like, this was skewed right, or there was a lot of values at high completion times, which makes sense because group R should have taken longer. So a lot of people missed out on like mentioning, because this was skewed left and there was a lot of values over here. You didn't even have to say skew. That's just a way that you could have gotten points for it. And so like justifying your answer with like, because the values were really high at the high value times, that makes group R the reason why I choose it. So most of the people, that's like what happened on that question. Really like particular and really easy to get credit off there. So then all of a sudden, so if you got an E, a P, or an I. So then you get a P, maybe on that one. So then part B, describe the histogram. This one was also pretty specific in what they wanted. So to be essentially correct, what you needed is, so I'll look at this part. So I'll come back to this. The shape is bimodal and provides a regional description of the distinct nature of the peaks. Oh, here's something else. I was just thinking about things that people were missing. It says, what would the shape be if we combine them? So some of y'all just said like, histogram 1 is skewed right, and then you said histogram 2 is this. It wanted to say, if they were combined, what would they look like? And so what they wanted to be essentially correct, you needed to say something how like, well, there would be this part down here talks about like how there's peaks at the beginning, like histogram 1 has a bunch of information at the beginning, and then there's not a lot, but then at the end, histogram 2 would bring in a bunch. So the picture would look like this. And you also, I think it says it somewhere, you could have included like a drawing as the like description there. So if you had a drawing like this, you would have got credit. And so for the most part, people got P on this because they really wanted you to mention this term called bimodal. So I guess going backwards, this free response overall was a pretty tricky free response like set of questions. So like just, and it is pretty specific on the rubric. So it's pretty hard, but bimodal just means how we have like bi means 2, so we've got 2 humps of data, like 2 clusters. And so bimodal, like some of y'all said symmetric, which is not wrong. It is like pretty symmetric. It's just they really wanted you to say bimodal just means like 2 peaks in there. And then they wanted you, if you said symmetric and you said all these other things, I gave you credit for this. So you needed both of these parts done, and so most of y'all fell into partial, where it was, you did this. You provided a description of the shape, but never used the term bimodal. So unfortunately, that's where a bunch of us fell into that one. So describe the shape. So the shape was a couple humps, clusters, and you could draw a picture when it's talking about that, or whatever. But so again, then you're either into an E, P, or if you just didn't combine them, you got an I on that section. Okay, and then C is we have our population, and we're talking about the distribution of the combined histograms. And it said it had a mean of 70, standard deviation 26.5. Here's another part where we messed up. It said we did a sample of 50, describe the sample distribution of the sample mean. So describe the distribution, but describe the sampling distribution. So anytime you're asked to describe the entire distribution, it's SOX. And then here's where, so some people did that and they said the mean is 70, which is right. But then they just restated the standard deviation. But the standard deviation, so a sampling distribution, if you remember, is like, here's my population, and the sample would be like, let me take one sample of 50 and here's its average. Let me take another sample of 50 dots from here and here's their average. Let me take another sample of 50 and here's their average. And what happens when you do that, if you have a big enough size, is it looks like this. And this came from the formula sheet. This was actually like unit 5 that we did in December/January. So it mixed the units together, where the standard deviation is equal to the population standard deviation over the square root of n, where we did samples of 50. So like this is the distribution for a sample size of 1, but this is a sample size of 50 from there. And so when I do a sample size of 50, the spread changes, becomes smaller, and all this different stuff. States that the shape is approximately normal, and justifying that because on a means problem, your sample size is bigger than 50, means that it's normal for a means, for an average problem. The proportions would be n times p, n1 minus p greater than 10. That would be like for proportions, but this is a means. So you needed all 4 of these to get an E on that section. If you got a P, it meant you got 2 or 3 of those 4 components. And so if you only got 1 or 0 of those, then you got an I. So kind of breaking down an E or a P or an I. And then thinking about it, I think I did on the rubric. They specifically wanted you to say like approximately normal when you're saying the distribution, and not like actually normal. It's like roughly, approximately. Like it's not. We're never gonna like guarantee like a perfect normal distribution. Like approximate. All right, so like, yeah, I'm just gonna go through them, and like maybe when I finish, just like if you have a question. So like over number 1, is there confusion on the key? Like why did I get that, or whatever? Just tried to read the key as best I could and give you all the answer. And then hopefully by doing it, the reason I want to give you a couple practice tests, and then the reason why tomorrow we'll start just doing a bunch of multiple choice and free response and looking at rubrics, is because the more you like see these all together like this, like all the units mixed together and the rubrics like this, I think the better you'll get. So I'm trying to get as much practice on it. So it's really easy to like fall off to the P category from an E. Even if you knew what you were doing, it's really easy to fall to a P. Or if you didn't know, it's really easy to go from a P to an I. So you can't really just fake it around the free response. So then here's the way the scoring works for the section. So to get a 4 is like the best response you can get on each individual question. You need all 3 parts E. So that's pretty tough to do. A 3 is 2 essentially and 1 P. So you need 2 E's, 1 P. And then 2, there's a bunch of different ones. So you could get 2 E's and an I. You could get 1 E and it was either 1 or 2 P's, or you could get all 3 P's. That would give you a 2. So if you just got a bunch of P's, you went down to a 2. If you got an I, so like this is pretty tough to get up here on the 4s and 3s. It's pretty easy to drop into like this section right here, where you got 1 E and like a couple or 1 or 2 P's. And then this would be like 1 E and 2 I's, and then this would be what, 2 P's and an I. And so if you got below that, you could get a 0 for the thing as well. So it's really easy. Like this is pretty tough to do up here. They make it tougher for a reason, and then it's like pretty easy to drop down to here and then quickly drop even farther from there. Okay, so, and then looking at the scoring as well. So a reminder, so this is a passing on the AP test. An overall score of 3 is 37 to 48 points overall. So that means like this is, you get 50 points for free response, 50 for multiple choice. So they understand you're probably going to be in this area, even if you kind of knew what you were doing. So like getting a bunch of 2s is probably putting you into like the 4 to 3 to 2 category, because they're reasonable. They know it's a pretty tough test. So if you got a 40 on the test, you technically pass an AP test. So they understand that it's really tough. And then it's like, what did I write up there? 49 to 60. If you get a 61 on an AP test, you've done the best you could do. So it's like they understand it's tough and they make it tough for a reason, to like distinguish people out. Okay, so that's kind of the scoring breakdown. And this is the general one for like every single one. Like they have parts, so if you got all 3 parts or all 4 parts E, you get 4. Okay.
Mr. Hanson, aren't AP tests normally based on like everyone who took the test? So if everyone gets 2s, then like they bump it up a bit, or like the highest person gets 5. It's like 20.
Yeah, I know that they do, like this number is not exact, but it's generally in that range. So that might be true. You know, I've never specifically really looked into it because it doesn't matter. Like if we just get the average, I guess, of like this is where most of the people end up averaging for 3s.
Mm-hmm.
That might be a true statement. But yeah, I know it's somewhere, this is generally the range of these values, plus or minus a few numbers. Though you'll never, yeah, it doesn't really matter the number in the end, I guess. Okay, so let me just keep going through these. Oh yeah, number 2 was, I thought number 2 was pretty tough. This was another like tricky thing here. And the rubric was so specific that I had to take off a bunch of credit on this for most people. So let me bring up my little rubric here. Okay, so what is the advantage of blocking? So first of all, let's just go through and make sure we're understanding what blocking means. So blocking in this case was the fact that I split based upon, let's see, they did a randomized block design, blocking on classification of runner. So what that means is they first split pro and recreational runners, then they randomly assign them to 2 different groups. So what we're talking about is why would they want to split pro and recreational runners? And what we're talking about is like different running shoes, which one does the fastest time. And so the 2 things you needed on this were a reasonable, so that's kind of vague, a description that blocking based upon pro or recreational is gonna help the like known variation of times. So what that means is if you said something like, we blocked, it's good to block because pro runners run faster than recreational runners. And so we don't want one shoe to have more pro runners than the other shoe have pro runners, because yeah, if I went out there and ran right now, I would not be very fast compared to someone who's like a professional. So we want to split because their times are going to be much faster than mine. Then we can compare shoe 1 versus shoe 2. Both those look like the same number. Versus each other in those different things. So that's what it means by like there's a variation in times. So you need to say that. And then I kind of said it there. Blocking allows for more precise comparison of treatment groups. So I kind of those kind of go together. Like if you said something like, yeah, like what I said, so if you block pro runners are going to be faster than recreational runners, so I want to compare each shoe for pros, each shoe for recreational to really narrow down which group's going to do best. So something, these kind of blend together, and there was a bunch of wiggle room in there, but something along the lines of helping our like data be more precise in that way. So kind of reading your score. And so if you got one of those, if I thought you got one of two of those, if you did an okay job of doing it, I said you got a P or an I. Number two, okay, we all did a similar error here. Why is it important to randomize? So when I split pro and rec, why is it important right here to do a random sample to 1 and a random sample to 2? Why is it important that this happened right here at this split? Okay, so the most common thing that people said is that it would help our bias, and then you went on to explain like if we didn't do this, a person might have their shoe that they run with all the time, and it would help them run faster, which is like a good explanation, but that's not what bias is. So what they were looking for here specifically is they wanted you to mention confounding variables, which is what y'all were talking about. Like it says by name or so this is basically saying, like, instead of saying bias, if you'd have said this helps us have these confounding variables, like a person being more comfortable in, I don't know, different types of running shoes. Nike, I don't think it's a very good running shoe, are they? But whatever, let's just say Nike, and then that would be a confounding variable because they're already more comfortable in that type of shoe. So that's confounding, not bias. Bias is in the type of like question that we're asking or the data that we collect, not necessarily randomizing people into like getting Advil or Tylenol. That doesn't help us with bias. So I think that this is what most people were meaning, but they didn't say confounding. So most people got marked off into like an I or a P in this category. And so on this little section, there's so much vocab that they could throw so many different types of free response questions with vocab that it can be kind of hard to do. But what it was is they wanted you to say like some sort of confounding variable. It helps us reduce. And a confounding variable just means like something we're like not accounting for. So that could be like the person already wears the shoe. I don't know, what are some others? People wrote different ones. I'm going blank on them. But just something that we're trying to help limit the stuff that, like when I said who does best on the AP test, well, maybe I didn't account for this person has a full-time job and this one doesn't. That would be something, that would be like an example of a confounding variable. So that's that one. So again, if you needed both parts to be essentially, if you only got one, you got partial. And then on C, replication. So replication just means that we did many, many trials, and that we could do more trials as well. And so one of the things that they wanted you to say was that how did we do replication in this one? It's the fact that we used 50 runners, right? Where did it say that? We did a random sample of 50 pros, and we did 50 recreational. So the fact that multiple runners were used, and then how does that, so that explains this one. And then what's the benefit? The benefit is that it helps us narrow in. If you said something like, it helps our statistics be more accurate, our statistics become more precise, because when you have an increase in sample size, your standard deviation in responses goes down. Like, you don't have to say this exactly, but something along the lines that, like, the more times you do something, the more precise your data gets. Like, yeah, the more people I sample their average height at Bryan High, the more accurate the data will get with it. So that's kind of two parts there. So in this experiment, they used multiple runners, and then that helps us become more precise, accurate data. So kind of that's there. All right. So then again, same thing. Three E's is a 4, 2 E's and a P is a 3, and then it kind of falls down from there. So, quickly falling down. All right. Then we got into some more math parts on number 3 and 4. So number 3, the distribution of ages of STEM majors at a university. So what we had is, what's the probability that the women selected will not meet the age requirement for internships? And they must be 20 or older. So if they are 20 or older, they're good. So who did not need it? All you needed to do was say these numbers are added together is, I think that was it. Yeah, 0.223. So all it said is, to get an essentially correct is you got it correct and you showed me some work. Like just circling those and saying plus would have been good enough. So most people got this one, E. Like this was, great question for everybody. But then part B we did not do as well. Okay, so what we did is we did a sample size of 100. So here we are. So we did a sample size of 100 women. What's the probability that at least 30 will not meet the age requirement for internships? So we just calculated this probability is 0.223. And so actually, before I go into the way I'm gonna do it, I saw a couple people do it a little differently and a little longer of a way and still got it right. But this is kind of the easiest way. It just doesn't say it very easily for what we want. But I have a probability of a single woman not meeting it is 22.3%. I did a sample size of 100, and I want to know what's the probability that at least 30, so 30 to 100, did not meet it. So what this is I have a fixed sample size, I have a fixed probability, and I want to know a certain range. So this is a binomial distribution, and then because it's a range, it's a CDF. So it wasn't very obvious, it was kind of hidden, and binomials are kind of already hard to identify, but this one was maybe not as obvious as it could be, but this was a binomial CDF. So one of the things was like, you said that it was a binomial, and you calculated it correctly, you showed your work, but it was a binomial CDF, sample size 100, P, you had a lowest value of 30, upper value of 100. And when you do that, it's something like I got 4.5% chance. Which, like, I can't remember. Mallory, was it you? Did you do some sort of like Z-score calculation here, or was that someone did something interesting that's like? Did you get it right or something? Oh no, someone did they actually got it right, and I was like, oh, like that actually makes sense. So like you could do it, or you could do a tree. Well, a tree would be a lot. But the easiest one is like we did a certain what's the probability 30 out of 100? So out of 100, fixed probability should kind of trigger some sort of binomial. The other thing, anytime they're doing one of the free responses is going to be probability, and you need to be on the lookout for either binomial or geometric, because they're very likely to put these into those problems, because these are like the tougher probability questions. Okay, so that was B. So kind of a hidden binomial. And then C was a pretty tough question, I guess, for us. So suppose a stratified random sample collected a sample of 30 who do not meet the age requirement and a sample of 70 who do. So basically what that means is they got 30 out of 100 for 30% for the stratified, is what that means. Like they got 30 who did not meet it and 70 who did. So 30 out of 100. Based on this probability, are they more likely, less likely, or equally likely to be selected from a stratified, so this probability, compared to a simple random sample? So this one was pretty tough, and I was even kind of, because I did it my own self first, and then I went and looked at the rubric and kind of went through it so I could get a good feel for the questions. So part A was actually just a random sample, like a random sample of people. So this is the probability from like a simple random sample. So what they wanted you to do is say that this is more likely because 30% is greater than the simple random sample of 0.223. So tricky. Yeah, just kind of all jumbled in together, and that's how they like to do it. So that's why I want to do a couple of these practice tests, just because they are tricky to see. Hey.
Hey, Mr. Hamilton.
What's up?
Is Audrey in here?
Yeah.
Yes.
Hey, Audrey. Mister.
Okay.
Hey, sweetie.
She won an award?
She got a scholarship.
Oh, she did. Wow, I was kind of joking.
Yeah. She really did. Surprise! And here's tickets for 2 guests.
Okay.
So, and here's the instructions. And if you want to share, it's going to be live streamed. If you want to share with all your family, they can watch you on YouTube. There you go. She really did get it.
Hey, you know, I don't think they did the like typically they've done like the student of the year for each class. I don't think they did that this year. I didn't have something for that. 'Cause that's normally at the awards as well. Like I remember filling out each year like
That's different
AP
awards.
stats student.
That's the like academic award. This
Was
is-
I thought it was always with the scholarship ceremony.
There's an academic award ceremony.
Yeah, there is.
It's when
Yes,
you're
there
like
is.
AP
Okay.
stats
Okay.
end of the
Maybe
year.
that'll be an
It
email
is
later.
different. I don't know.
Okay.
I haven't heard about that.
Okay.
I need to ask. All right. Let me see if I have any other kiddos in there.
I can give it to Blake Falden.
Yeah.
Yeah, he's my student of the year. He's in love right now, so I never see him.
Oh really? Juicy. I'll talk to him about that.
Yeah. Hey guys.
Hi.
Have a good one.
Okay. What scholarship did you get, Audrey?
Yeah. They don't,
yeah.
That's what she's gonna get like.
Oh, that's kinda fun.
I got one.
Yeah.
But you know you got at least one.
Yeah.
You could have got
Did you get
multiple.
Yes.
Okay.
I don't think so. Is that like 7? I'm
Not
going. I want to go now.
I remember
That's
some
kind of
years ago when
fun.
I
It was
was my
kind of
brother
lame in high
lasted
school.
like
They
2
would already
hours,
tell you
and it
what
was
you
just
got,
like
and then you just
they
went
were-
and like.
And then like the memorial
So that's kind of
scholarships,
fun.
they
You
would,
don't
like,
know, and then you
like,
just sit there and you're like.
and then
Okay.
but they're gonna say Audrey gets a $25 gift certificate to Harvest Coffee.
Ooh, Harvest.
That'll last you like 4 drinks. I
That's
hate
true.
it.
That's anywhere though, right?
You could
Are
do
you starting to work at Starbucks yet?
I start next week.
Okay, let's keep going. We got 3 more. So number 4. This was another calculation one, and it was hit or miss on this one. Hit or miss with how we did. Okay. So on this question, there are there are 4 parts that you needed. Actually, on part A alone, there were 3 parts that you needed to get correct on each of these. The first one is that you needed to do the conditions before you did anything. And so you can see, like on section 1, it says identify that the random sample condition is met and that the population is normal. And so you needed to say like random sample, check. And then we're talking about the mean number of steps, and we did a sample size of 61. So you would say it's a normal distribution because 61 is bigger than 30, it's big enough. So you needed to do that. If you didn't do that, you automatically got marked off down to like a 3 as your best score. Then, let's see, so 99% confidence interval. So let me just go through this because I think we need it. So let me just give myself some room here. So let me do the entire confidence interval. A confidence interval is the average that you got. In this case, we're doing means. So the sample mean plus or minus the, I'll write it up here, the critical value times standard error. So in this case, the critical value is one of 2 things. It's either a Z or a T. You use a Z for proportions, and you use a T for means. So this was a T distribution. Z for proportions, T for means. So when I'm doing a 99% confidence interval, and I've got a degrees of freedom, because when you go to the T table, it says degrees of freedom is 61 minus 1, so 60. You look up degrees of freedom 60 at a 99% confidence interval, match the row and column, and the rubric did 2.66 would be the T value. And then standard error, the formula sheet, I'll just write it. So like on the backside formula sheet, it says standard error on the far right for one population mean looks like this. Standard deviation over the square root of n. So it would be 21313 over square root 61. So, and then this is 797 steps. So you do this, you plug it in, you get your number, and it's something like, there's a little wiggle room on the rubric for rounding. Like you could have rounded instead of doing decimals and got it right. But you get something like that. You either say the decimal or you say 9,009, 10,585. So so this was one part. This whole thing right here was one part. And then here's where another group of people miss points. It says to interpret. It says calculate, so that's a check for calculate. And then it says interpret. So interpret would mean I would say or you could say I am, or we are 99% confident the interval, and you would say this interval contains, and then you would say the question, contains the mean number of steps on a typical workday for all people in New York City. So you would take this green part here and plug it in right there. So you had to have a bunch of different parts, let alone get the actual thing right. Don't miss when it says justify or interpret. So like on number 1, it said justify, and you really needed to justify. Or when it says interpret, you gotta like spell it out in words what it means. This is like not a normal math class. There's so many words you gotta use. So more of like a, what did I say? It's like a science. It's like biology or psychology, anything like that. You're testing people's minds and thoughts, or what they do on a typical day. And so you needed all three of those parts to be like on there to get credit. You got a point for each section. And if you got it partially correct, you got like half a point for each section. So, and then part B is they want to know whether it's unusual for one person working in New York City to get approximately 8,500 steps on a typical workday. Is it appropriate to use this confidence interval that we found in A? So this one was tricky because I need to erase all my stuff here, because this confidence interval that we got is for all people. So the number we got was for all people working in New York City would have like a mean of 9,000 to 10,000 steps a day. But that's what we were saying the mean was for all people with an activity tracker. Part B is really tricky because it snuck in right here. Is it appropriate to use this interval for one person? And our confidence interval was talking about all people. So you would say, like, it cannot be used because intervals are not about individual data values. So you had to say something like it's not because that interval specifically was for a range of people, specifically all New York City people. And this was just asking for one person. So, after I did this 2 or 3 weeks ago on my own, and after I did it, I was like, man, this is gonna be tough. And I debated giving y'all a different free response, but then I was like, well, it'd be good to see a really tough one. So this one is really, all the questions have little tricky parts with them, so you gotta watch out for them. So one person, not all. Okay. Cool. All right, then number 5. The first question was circle the point on the graph who won the race and approximate the total race time. So a bunch of people just circled a point without giving me an approximate. Some people just didn't give the right time. So who won the race? It was kind of close between this person and this person right here, because this is how fast did they run compared to how quickly did they jump out of the blocks. And so this person right here was like 9.7 plus like 0.13, so that would be like about 9.83 something. And this person was at 9.6 running time plus 0.15, which comes out to about 9.7577, because it's a little bit above. So you could say like 7.5. There was a range that you could give. But this person was the winner, which most people got. But this was the actual time that they ran. It was actually a combination of how much running time did they have and how fast was their, how long did it take them after the the horn blew or whatever, the gunshot, to actually start running. So here's their running times. Here's how long it took them to actually start after the thing blew. So we want to have a quick reaction time and fast running time. So this is just a plot, people who react late, they also run slow, I guess, I don't know. And the people who react fast also run fast. So you just needed both. Okay, B, based on the graph, is it reasonable to assume that these things are independent from each other? And so what it was is that it's not reasonable because like this pattern, there's a very, you didn't have to say it exactly like this. When I did it, I actually said there's a strong linear association. They said there's a clear positive association. So I said like a strong, you could say like a strong positive association, whatever. But these are not independent because it seems like on our graph, there's a very clear, like you're very fast if you start fast. And if you start slow, you're pretty slow. Like it seems like there's a pretty clear like distinguishment there between the two. So you need to say both of those. If you said something kind of, so if some of you said like it's not reasonable, but then you said something like a weak justification, then you got a P. So like if you just said like because the graph kind of goes up as it goes up, that's not quite saying the same thing. It was just really tricky, like very specific on like on this scatter plot because some of you said like as you go up on this, you go up on this. That's basically the same thing, but they wanted you to say like positive, linear, things like that. So the duffs, like positive or negative, linear or curved, and is the correlation strong or weak? And so description words like that to get an E, and then if you drop down from there to a P. And then based upon your score, again, you're getting like a 0, 1, 2, 3, or 4. So hopefully you can clearly see like, oh, I got a 3 because I checked the boxes. Oh wait, there's still one. C. So then based on the model, explain why the use of extrapolation to predict 0.30 might not be appropriate. So basically, because 0.30 is outside of our graph, and that argues the model. So basically, it's outside of our graph, and we don't know what happens outside of our graph. Like, it's unfair to know if the model, if the thing starts going like this, or it goes like this, or it goes like this. Like, we don't know. This out here is a big question mark. What happens? So if you said something along the lines of that, it's outside the graph, and it's a question. Okay. All right, and then our favorite question, you've done all year, probably. Some of us loved it so much we just stared at it and ended up not writing stuff on there because we were so in love with the question. So number 6, it is an interesting question. It does start in something that we know. You might not know it, but we do know it. And then it moves slowly away into something very weird by the end of the problem that I've never heard of myself. Chebyshev's inequality. But like, it's something that you could actually get to. They've given you enough information to get there.
Are they gonna do that?
Yeah,
Like,
number 6 is always starting in something you know, and then it slowly moves into, it makes it a very weird looking problem, but it's actually possible. There's a route for you to do it. Though if you don't start, if the thing that you should know you don't know, then yeah, it becomes a really hard problem. But it spells it out enough in the paragraphs, kind of, for us, and if you use the formula. So let's go through it. The other thing about this is number 6 is worth 25% of the 3 response questions. So it's a big problem. So even if you get like a 1 on this, it's basically like getting a 2 on every other question. So if you could scratch out like getting some credit, then it's really good. Like getting a 1 or a 2 is actually really, really good. to get on number 6. Okay, so let's start on this first one. One condition. So what we have up here is we had like 400 light bulbs and 44 were defective out of the 400. So I had 44 out of 400. These are just things that like I'm noting as I'm reading the paragraph. 44 out of 400. Oh, that's a P, specifically a P hat. If like I'm just looking at my own notes, like that's some things I'm jotting down. So one condition is that the distribution is approximately normal. Is it reasonable to see that this is met? So how do we do the normal conditions for a proportions? So for means, it's that it's bigger than 30, but for proportions, it's n times p, n times 1 minus p bigger than or equal to 10. And so, let me see. So I was looking on the rubric to see if they justified it from there. Yeah, so what you can do is it's 400 times, I'm missing something on here, yeah, so up here at the very top, outside of, like in the paragraph up above this, it says, we wanted it to be greater than the 10%. Is it greater than 10%? So on this P, you could have either used 10% or this comes out to like 11. You could have used 11% there as well. 400 times 89%. Is it bigger than 10? So for this section, there's parts A, B, and C were the first section. So on part A, if you said that you should assume it's correct and gave a good justification, that would be like, check there. Part B, what's the standard error? So please look at your formulas. It's on the formulas sheet. The standard error is that, how is this calculated? So on the formula sheet, there's a whole column on the right side that says standard error. And this is a standard error for a 1 proportion. There's only one sample. So the formula sheet says square root of P 1 minus P over N. I guess standard error actually says P hat. So formula sheet shows us that. So then if you just show 11%, 1 minus 11% over, what was our sample? 400 there. That gives you that 0.0156. So this is something really familiar. Like part A is just doing, we did normal distribution conditions all year, like all spring. I did this normal distribution condition check. And then we did the standard error formula. It's just when you see it, you just kind of go blank sometimes. And then part C, this one is something also familiar that's asked in a way that might make it hard for you to comprehend. How many standard errors are you from this value, from 0.10? So what this is actually saying is, another way to look at it is like, how many standard deviations am I from the mean of 0.10? So what that hopefully triggers, how many standard errors, standard deviations from the mean. We did that all year as well. It's like the z-score, where you do your test statistic minus the mean over standard error, which was that number that they gave to us. And so I think it was like 0.64, 0.64. So all those are very like possible things. I know it's been, at this point, February. Maybe February is when we were doing a lot of confidence intervals and proportions stuff on its own. but like that's where that started. So section 1 was the part where you could really get a lot of credit. So like doing a normal calculation, doing the formula, computing it correctly, and then getting this value. So if you did each of those, you got an E on section 1, which means you're guaranteed to at least get 1 point, which is great. So it just, all these things are like things we can do. It just asks it in weird ways. Like it might not have been obvious that it's a z-score, but that's what that was saying. It just asks it in tough ways. Okay, this next part, we had this other value, y, that had a 104 out of 400 possibility, which is 26%. So that's for y. And it said that y had a standard error of this. Alright, this is where it starts becoming really weird. All of a sudden they're like, okay, D, this is D. This like px plus py over 2, and it's like, I've never seen this in statistics. Like, what did my teacher do? What is this? This has gone into somewhere else, but if you understand these little parts, px is just that 11%, py is this number up here, and then you just divide it by 2. That's how you calculate D. And so it's like this. So like this has gone into somewhere weird that we've never, like we don't necessarily go over, all because it starts having a huge paragraph and it D hat, it's like what the heck, weird symbols, but it's really nothing crazy. It's just they're trying to throw stuff at you to make it look crazy. So they gave you everything you needed here. And then part I, it asks you to do the standard deviation, the standard error of the combined things. So when you combine, this one was kind of tough. When you combine two standard errors or standard deviations together, remember we have to do the standard deviation squared added together and then do the square root. Or you could have done this. Some people did this, like p of x, 1 minus p of x over n plus p of y, 1 minus p of y over. You could do that. Either way, when you do that, either of those, the tricky thing about this is that part D, the formula for D had those two added together and then divided by 2. So you're supposed to do these things and then like divide by 2 is kind of the tricky part of this. So some people got like 0.027, which was so close because that would be what this is, but you divide by 2 and the correct answer was like something like this. So just close to what we've done before, it just starts going into weird areas. And then we get really weird on this next part. So then all of a sudden I've got W, D hat, which I didn't get that right in section 2. I was lost over S of D hat, and I'm like, where is this? Minus 10. But you just take those from what we had. So this value up top, I got this. I'm putting in the thing. S of D is what we did right there. So I put it in here. A note is if you put in like the wrong number here, if you just like got the wrong number on part E and F and you just put them in here, you would actually not get counted off twice. You would you'd be counted correct. Like let's say I had 12 and 0.02, but I would actually get credit for like continuing the problem just with my wrong numbers, because they're like, oh, you at least did this section right, like you plugged in the values. Okay, so let me just keep going on this. So you get this sort of value here, which at this point when I was doing it, I'm like, where are we going with this? I've got this weird number. I myself was also confused. Then it says Chebyshev's, that can't be right. Chebyshev's inequality says this, and it says 1 minus 1 over k squared. And so what happened here is it said use the value of w to decide. So what you do is you actually take this formula and you plug in the value you got for w, and that was like this value, and you square it. So like all I did is I kept just continuing with my numbers. I just took this number and took it down to the next problem. And so you get some number, specifically like something really high, like in the 90s. And it asks you, at a significance level of 5%, is there statistical evidence that we're greater than 10%? So this is where it got, or this is where it was kind of hard as well. I mean, all of it. At this point, we're very in the weeds on this problem. But what this number actually represents is a test score of like, we're testing greater than 10%. This value is all of these, and we're testing at an alpha of 5%. And so this little shaded region would be 1 minus that, which ended up being, what is that? 2.5, yeah. So 0.025, and so you actually, 0.025 is less than alpha, so you have evidence. So that was a really long, drawn out, weird way to all of a sudden get to something about significance level. So you have some sort of conclusion at the end, and you get some sort of big value. If I ever get like a 90 value and I'm trying to compare it to a small value, something should trigger off in my mind that I should probably do 1 minus that value. And it should be at least close to 5%. If it's that much bigger, like something should trigger off in your mind. But number 6 was, yeah, so it started pretty reasonable, then it slowly moved into kind of reasonable but a little strange, and then it moved into this, which could scare you into something that's like, what are we doing? But if you get at least 1, or you get an E and a P, you get like a 2. And so if you're getting at least some of these things on number 6, it's important. So I think the main thing when you're going through it, as I've been going through it, is the importance of understanding all the, like using your formula sheet and understanding what all the formulas are, not just in how to use them, but what the words actually mean. Like on this case, we know a z-score, but do we know that it means like how many standard deviations from the mean, like standard errors from the mean? So they really test you into like your knowledge and the combined knowledge together. So just because a problem starts as a confidence interval or as a like whatever problem probability, it doesn't mean it's going to stay there. It can ask you anything of the entire year in one problem. So they are tricky, and there's a bunch of different parts to them, and the rubric is super specific, but they give you wiggle room to like get a bunch of partial credits and still pass the AP test. But just being as specific as possible and knowing your formulas, those are the kind of the key to these. So we're going to do some more free response practice, multiple choice practice, and then we're also going to take another mock test. And we'll just kind of keep going with it and